This is PreCalculus 12, Chapter 8.1. Counting and probability is a field of mathematics called combinatorics. We will study combinations, permutations, Pascal's triangle, and the binomial theorem. Now, counting is much harder than most people think. So we start with the fundamental counting principle. If there are n different objects in one set, and n2 different objects in a second set, then the number of ways of choosing one object from each set is n1 times n2. And we can apply this to multiple sets. It applies to what we call independent events. That is, each event has no impact on the next event. Let's look at some examples. How many ways can we pick one card from each suit in a regular deck of cards? Now we have to note that each suit is independent of the other suits. There are 4 suits in a deck of cards and 13 cards in each suit. If the events are the same size, that is, number of choices, we can use the number of choices raised to the power of the number of events. So we would have 13 times 13 times 13 times 13. 4 suits, 13 cards in each suit. And because the number of choices is the same, and there's 4 events, we can change it to 13 to the power of 4, and this works out to 28,561. Let's look at another problem. How many ways can we pick one card from the reds and one card from the blacks in a regular deck? 2 suits are red and 2 suits are black. So we would have 26 cards to choose from that are red, 26 cards to choose from the black. And this is 26 to the power of 2. Note that picking the red card doesn't influence how we pick the black cards. And this is called independent events, when one event has no impact on the next event. And this works out to be 676. A tree diagram can be used for small cases. We draw all the nodes, then we count the leaves. And the trees are drawn upside down. This generates what's called a sample space. So it shows all the possible outcomes. So here's an example. Draw a tree for flipping a coin 3 times. And we note that each flip is independent. So regardless of whether we get heads or tails on the first flip, that does not impact whether we get heads or tails in the second or third flip. This is the root. And our first outcome could be heads or tails. And our second outcome could be heads or tails, but we write the first one as well as the second one. And then we have heads or tails again, but we add the first one. This is one way of doing it. And again, heads, tails, heads, tails, heads, tails, heads, tails. It's just alternating. Heads, 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 tail, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. So this is a quick way to generate all the possible different combinations that we can get heads or tails. These are called nodes, and these are called, the lines are called branches. And these are called leaves. They're at the lowest level. There's no more branches sticking onto leaves. The first line, we have two choices, heads or tails. The second line, we have only two choices, heads or tails. And on the third line, we only have two choices, heads or tails. So there's 8 ways. And if we count the bottom line, 1, 2, 3, 4, 5, 6, 7, 8, there's 8 ways. The pigeonhole principle is a very simple principle, but it's very powerful. If there are n items and m pigeonholes, and n is greater than m, then at least one pigeonhole contains more than one item. So the way we prove this is by proof by contradiction. We'll say that there's 4 items and 3 pigeonholes. Let's draw the 3 pigeonholes. 1, 2, 3. We assume that they're not going to have more than one in any box. Let's just use the numbers 1, 2, 3, 4. So we'll put 1 in the first box, 2 in the second box, 3 in the third box, and we have the fourth one. We have to put it in one of these boxes. They're all full with something. So now one of them contains 2. So by contradiction, we assume that all of them were going to be in their own box. By contradiction, more than one has to be in one pigeonhole. Okay, let's look at an example of how to use this. How many regular dice must be thrown to ensure a match? Each die can be 1 to 6. So that's how many pigeonholes we have. So by the pigeonhole principle, 7 dice must be thrown. The minimum. So as long as n is greater than m, then we can use the pigeonhole principle. Here's another one. So how many combination locks can the lock company make before there is a duplicate combination? So the locks use 3 numbers, each from 1 to 30. So each number is independent. So we have 30 times 30 times 30. So one number doesn't depend on the next number. So this is 27,000. So by pigeonhole principle, we need 27,001 before there is a duplicate combination. Let's look at some backwards problems. A slot machine has odds of 10,648 to 1 of getting a jackpot. If there are 3 reels on the machine, how many stops are on each reel? And when we say stops, those are the number of icons on each reel. Okay, so we have S cubed. That's the number of stops. There's 3 reels. Each reel is an event, and each stop is a choice. So we have 10, 6, 4, 8. So to calculate S, all we need to do is the cube root of 10, 6, 4, 8. And that equals 22 stops. Okay, if you get a non-integer answer, if you get a negative answer, you've done something incorrectly. These problems should work out to a positive integer. This problem is using the fundamental counting principle. So here's a separate way of phrasing it. It's a little bit harder. A slot machine has odds of 537,824 to 1 of getting a jackpot. There are 14 stops on each reel. How many reels are there? Okay, so the stops to the power of reels equals 537,824. And we know that there's 14 choices. We don't know the number of reels. We don't know which route to take. However, we're trying to find the exponent. And this is going back to chapter 5. So we need to take the log. So r log 14 equals log 537,824. R equals log 537,824 divided by log 14. And that equals 5 reels. And again, we are using the fundamental counting principle. Now, again, we should get a positive integer for an answer. If you don't, then you've done something incorrectly and you should check your work. Next page. A restaurant offers combo meals, so you can choose a cheeseburger, chicken strips, or a cheese pizza. Then you have another choice, fries or onion rings. Then you have another choice, pop, milk, coffee, tea, or juice. And then you have another choice, ice cream, pie, or cake. How many different meals can we make? Each choice is independent. And we're going to create a partial sample space. And like I said, this tree diagram only works well for a small number of choices. But we have a large number of choices. Cheeseburger, chicken strips, cheese pizza. Then we have fries or onion rings. Notice I'm not putting the CB here. CB here is going to get really long. Fries, onion rings, fries, onion rings. Now we have pop, milk, coffee, tea, or juice. And I don't have room to do that for all of these. Pop, milk, coffee, tea, or juice. Pop, milk, coffee, tea, or juice. And then after we pick our drink, we can pick our dessert. Ice cream, pie, or cake. Ice cream, pie, or cake. And we just do this all the way along. Ice cream, pie, or cake. Ice cream, pie, or cake. So we can read our choices, assuming that they're all complete. You can go down this way, cheeseburger, fries, juice, and pie. Or you can go down this way, chicken strips, onion rings, pop, and ice cream. And then you would have to count all the leaves down here. Now we don't want to do that. We want to use fundamental counting principle. So the first one, we have 3 choices for our entree. We have 2 choices for our side. We have 5 choices for our drinks, and we have 3 choices for our dessert. And don't need a calculator. If you multiply strategically, it simplifies our calculations. 2 times 5 is 10. 3 times 3 is 9. 9 times 10 is 90. Okay, sorry, this is the wrong word here. We should say dependent. So dependent problems. These are slightly different because the number of choices won't stay fixed. So here's an example. How many ways can 3 cards be dealt from a deck of cards? And we want to note there will be fewer cards with each deal. So this is a dependent event. So we have 52 cards in a deck. Once we've dealt a card, there's only 51 cards left in the deck. Once we've dealt that card, we only have 50 cards left in a deck. So it's not 52 to the power of 3. It's 52 times 51 times 50. And this is 132600. So don't use formulas blindly. Determine the number of choices, such as dependence. And when you're ensuring a match, it's likely that you're using the pigeonhole principle. And for those of you who don't play cards much, a deck of cards has 52 cards. 26 of them are black, 26 of them are red. There's 13 spades, they're black. There's 13 hearts, they're red. There's 13 diamonds, they're red. And there's 13 clubs, they're black. And we have ace, and then we have the numbers 2 to 10, the jack, the queen, the king of each suit. And these are called suits. Spades, hearts, diamonds, and clubs. And if you are into numerology, we have 52 weeks in a year. We have 13 weeks per season. We also have 13 lunar cycles per year. And if you count this as 1, and then we have 2 to 10, 11, 12, 13. If we sum up the numbers from 1 to 13, it's 13 times 14 over 2. And you would have done this in arithmetic series. We have n times n plus 1 over 2 to sum up a series. And then we need to multiply this by 4. And you get 364. If you add the joker, we get 365. That's the number of days in a year. If you add the second joker, we get 366 days, which is the leap year. So, is that what they had in mind when they made a deck of cards? Not sure. There's no history to corroborate this, but it's a nice coincidence. So if you're trying to memorize some of the numbers, you can use the calendar to help you remember. And that completes this lesson.